It is
Good.
on.
Ok. Bueno, bienvenidos a todos una vez más a nuestra sesión de charlas semanales. Tenemos el día de hoy la presencia de un nuevo colega. Su nombre es Pedro Bairrão. Él es magíster en física por la Universidad de Sao Paulo y ahora mismo se encuentra haciendo un doctorado en la Universidad Estadual Paulista, en particular en el Instituto de Física Teórica. Bueno, un poco más sobre Pedro es que, bueno, él trabajó y actualmente está trabajando en teoría de cuerdas. Tiempo atrás había hecho un curso llamado Iniciación Científica en Sao Paulo también. Y bueno, sus áreas de investigación relacionadas son gravedad cuántica y bueno, el formalismo de Palatini. Bien, entonces debido a que nuestro invitado es extranjero, vamos a hacer la sesión en inglés, por lo cual, bueno, a partir de este momento vamos a cambiar todo a inglés. De todas formas, si es que las personas presentes quieren hacer alguna pregunta en español, pueden hacerla y nosotros nos encargaremos de traducirlo al inglés y hacerle pasar al expositor. Well, I think that we can start, Pedro. So feel free to start and well, good luck with that.
Okay. Thank you. Thanks a lot, Dennis, for the introduction. Before I start, I'd just like to quickly thank everybody who's organizing this event, and you in particular for inviting me in person. I'm very happy to be here giving this presentation, which is about a topic which I find very interesting, which is AdS CFT. Now, the idea of this presentation is to give you a very heuristic overview of this topic, which can get very dense. Anybody who's already studied this a little bit, or string theory, or even field theory, might find some parts of the presentation a bit boring, because I've tried to make it so that you need a minimal background in these fields and still get a general idea. So my idea is to give a very, very rough idea of the main points of this topic. Whoop. Oh, okay. So to start, AdS CFT, and I'll go over what these letters mean at the end, but for now, just take it as a name, also known as holography, is a subject that connects quantum field theory and string theory in a very unexpected way. So the rough picture is that you have field theories, which are the kinds of theories you use to do particle physics in, say, d dimensions, but we usually worry about 4 dimensions, 3 spatial and 1 time dimension. And this is dual, in a sense that will be clear later, to some string theory, which are usually thought of as quantum gravity theories, in d+1 dimensions. Now, this can be a very powerful tool because using this duality, complicated problems in QFT, and complicated in this context means that nobody knows how to solve them, at least analytically, they can be mapped to simple problems in string theory by using this duality. And the question I want to answer, or at least motivate here, is how can this be possible? So how can string theory and field theory be not different theories, but different languages for the same underlying physical system, which is what this is about. So my plan for this is to talk a little bit about quantum field theory, but only the most basic ideas, Feynman diagrams, basically, and also the field theory that deals with the strong nuclear force, which is the force that binds the quarks inside the protons and neutrons. Then I'll talk about something called the large N expansion, which is where you can find the connection with string theory. I'll say some words about string theory, and then finally, I'll say some very simplified, I'm not going to go into the details, but I'll talk a bit about what AdS CFT is. Quantum field theory, or QFT, is the theoretical basis of particle physics. So the idea is that if you have some quantum theory that's defined by the quantization of some classical theory, and this classical theory has an action in the sense of Euler-Lagrange equations, you vary the action, you get the equations of motion. For fields, usually the action is some integral over spacetime. So this is why we have an integral d for x here of the Lagrangian. If you have this for a classical system, then if you want to quantize it, or that is promoted to a quantum theory, the quantum probability to go from a state I, initial state, for the system to go from this initial state to some final state F, is this P, I goes to F here. And this is the absolute value squared of this A quantity, which is a probability amplitude. And the way you compute this thing is with this following formula here, which says the following. You sum, to get the amplitude to go from I to F, you sum over the amplitudes of all intermediate states M. So M is just some evolution of the system which interpolates I and F. So if I have a particle which is at some point, and you want to know what's the amplitude to find it at another point, you can calculate the action, or the amplitude, sorry, for it to go in a straight line, or do something like this, or it can move around the Earth a couple of times and then go to the final position. Each of these possibilities will have an amplitude associated to it, and you add them all up. And that's the full amplitude. And the way each of these amplitudes is computed is with this exponential of I times the action. S here is the action, and h bar is Planck's constant divided by 2 pi. So this is where the action enters. And these probability amplitudes satisfy very similar properties to regular probabilities. So for instance, if you have two independent events, A and B, the amplitude for A and B is just the multiplication of the amplitude for each one. So this is a rule of probabilities, and it's also shared by probability amplitudes. Now, if you apply these ideas to fields, what you get is quantum field theory. And if you use quantum field theory, you can discuss relativistic particle dynamics. So for instance, you can describe these kinds of processes here where you have, for instance, two electrons which move close to each other. Time here, in all my drawings, time will flow horizontally. So here the two electrons come close to each other, they feel the electric repulsion, and they scatter and have some final state where they're going away from each other. So the amplitude for this kind of process is something that quantum field theory is very well equipped to give you. So this works beautifully for electromagnetism, and a couple of years later, people learn how to generalize it to the weak and strong forces as well. And as you may have heard, gravity is a lot more complicated. So there are nuances. I'm not going to really go into them, although feel free to ask. But QFT and gravity are more delicate to combine. So the particular QFT model that describes the strong force in particular is called quantum chromodynamics, so QCD for short. So when you specify a theory, a quantum field theory, you'd need to say what are the basic particles. For QCD, these are the quarks and gluons. So these are among the elementary particles of the standard model. And QCD as a theory is somewhat similar to electromagnetism, but you also have some very important differences. And it's similar in the sense that you have charged objects, which would be the quarks, and you have some field, like the electromagnetic field. You can have waves on this field and things like that. And the field, in a sense, carries the force. The force travels at the speed of light. So in that sense, it's an electromagnetic-like theory. But first of all, there is a conserved quantity called color charge in QCD, which people call red, blue, and green. These are just names. What's important is that there's 3 of them, which is somewhat like electric charge in the sense that you can have red, anti-red, blue, anti-blue, green, anti-green, but you have more than one. So this is already different from just having positive or negative charge. Quarks carry this color charge. And the hadrons, which are things that are made out of quarks, like protons and neutrons and pions, they are color neutral. So if we think in terms of colors, they are white. Gluons, which are the equivalent of the photon, so the equivalent of the electromagnetic field itself, also have color charge. So this is very different from electromagnetism, where the photons, or you can think of them as electromagnetic waves, they're not themselves charged. They just carry the force from one charge to the other. Here in QCD, the field itself is also charged. And this is a major source of complexity for the theory. And related to this is the fact that the strong force between two quarks grows with the distance. So if you have two quarks and you try to separate them, instead of the force becoming weaker, like for instance between an electron and a proton, it actually grows stronger, and this leads to confinement, which is basically the fact that you don't find lonely quarks in the universe. They're always paired up, because if you try to separate them, the force grows. So for simplicity here, we're only going to talk about gluons. We're not going to talk about quarks. So this is basically like electromagnetism in a vacuum, no charges. This is just for simplicity. You can do this with quarks as well, but this is just the most simple setting for the discussion. So we're going to talk about gluon amplitudes. And the amplitude for gluon to propagate from some point x to another point y is, by that formula, the sum over the individual amplitudes for it to go from x to y in all possible ways. So here, for instance, you have the first contribution, which is to go, this coiled line is how you represent a gluon propagating. But it's going in a straight line. It's not going around the cycle. This is just a way to do the drawing. It's like a spring because of the strong force. So this is the first contribution. You have a direct propagation going straight from x to y. This is one possibility. You have the second one also, where the gluon goes from x to z. Z is some intermediate point. It then splits into a pair of gluons. Each one propagates a little bit. They meet again, combine into one gluon at this other point w, and then this one gluon goes all the way to y. This is a possibility of quantum field theory. You can have these kinds of decays or joinings of particles, and it also has some amplitude. And you also have an infinite set of other interactions which I haven't, other contributions which I haven't written here, where you have more splittings and more joinings and all kinds of things. So in equations, this means that the amplitude for the gluon to go from x to y is the amplitude to go directly, to decay into a pair, which then rejoins, plus dot, 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 where dot, dot, dot means basically every other possibility. But since the amplitudes multiply for separate events, for independent events, this diagram can be split into the multiplication of the amplitudes for each process happening. So you have that the amplitude to decay into a pair which rejoins, which is the second diagram, is given by the amplitude to go from x to z times the amplitude for decay, which happens at z. This is squared because the amplitude for rejoining is numerically the same as the amplitude for decay. This is a consequence of the equations of motion for this field being invariant under time reversals. So splitting and joining are time inverses of each other. So we have just the square of the decay amplitude to account for the decay and the joining. You have the amplitude to go from z to w, which are these propagations in the loop, squared because you have two of them, one above and one below, and then finally the amplitude to go from w to y. So this is how you compute these things. And of course, you need to know what the basic amplitudes are. The amplitude for propagation, for instance, this one, and the amplitude for interactions. Here you have what I've called A of decay. So these are the ingredients you need in order to build that expression and figure out the amplitude associated to that diagram. That's an example of a Feynman diagram, by the way. And to find those basic amplitudes, you use the action. The amplitude for propagation is called the propagator, and the amplitude for things like decay are called vertices, because it's where many propagators meet. So it's like a vertex. You get them from the form of the action for the fields. So this is the action for the theory of gluons. I'm not going to need a specific form of it, although uh, if you have studied the covariant formulation of electromagnetism, this may seem familiar. But what's important here is that this action contains this G in front. And G is what's called a coupling constant. It's a number, it's a parameter of the theory. And it turns out that once you use the rules of QFT to extract from the action the basic amplitudes, the propagator ends up being proportional to G squared. The vertices for this particular theory, there are two, vertex with 3 legs and a vertex with 4 legs. These come out proportional to 1 over G squared. So each propagator adds G squared to the diagram, because it would be a factor of this. Each vertex adds 1 over G squared. But every vertex comes with some propagators, because you need lines to go into the vertex. So as a whole, you have that more interactions, meaning more instances of decays, of rejoinings, things like that, will lead to a larger power of G in the diagram, meaning in the amplitude. If G is small, here small means smaller than 1, then the more powers of G you have, the less the diagram is going to contribute. The amplitude for this process is going to be very small. So if G is small, you can just keep the first couple of diagrams, the ones with the least amount of vertices, and the others you can discard. So this is perturbation theory in QFT. Perturbation in the coupling. G is called, again, a coupling constant. The problem is that in QCD, G actually grows at low energy. This is a parameter that actually effectively depends on the energy scale where you're studying the process. So if you study low energy phenomena in QCD, you will learn that G becomes large. It becomes larger than 1. So for energies smaller than this lambda QCD scale, which is approximately 200 MeV, G becomes larger than 1, and the theory becomes strongly coupled, meaning that perturbation theory is not going to work. Because if G is large, then you need to add the diagrams with more interaction splittings of the gluon and such that you add to a diagram will make it more relevant, because G is large. So of course we can't do this. So perturbation theory breaks down, and we don't really know how to do computations of QCD for low energy phenomena. And low energy here means like hadronic physics. So that's the situation with QCD. So you'll need a new idea in order to overcome this problem. And one idea, which was due to with Hooft, is the so-called large N expansion. We can try to use the number of colors, the color charges, red, green, and blue, 3, which here I'm calling N, but for QCD, N is equal to 3. We can try to use that as an expansion parameter. If you can't expand on the coupling, because the coupling is large, then maybe you can expand on 1 over N, because 1 over N is something which is smaller than 1. Now, of course, it's not guaranteed that something like this will work, but it might work. And it turns out that it does work. So now I'll move into how that works. Now, gluons carry color. Recall that I said that they were charged under color, differently from photons. So gluons carry color anti-color charge. So for instance, you can have a gluon which is in a particular state, which you would call red anti-blue. So if you look just at the color, they are like a quark-anti-quark pair. They're not actually a quark-anti-quark pair, but looking just at the color part, they could be mistaken. So because of this, gluon diagrams can be written with this kind of double line notation, which is just going to substitute the coiled line notation. And here you write two lines with arrows going in opposite directions, and the arrows represent the flow of color charge. So this arrow above here in this gluon propagator could mean red, traveling along this direction, so to the right, and the arrow below has the opposite direction because then you have the anti-color, so it could be like an anti-blue, and it's oriented oppositely because an anti-color degree of freedom is like behaves in a sense like a color degree of freedom going in the opposite direction. But again, this is just a notation, but it's going to be useful. So here we have the propagator and the three vertex using this different kind of notation. So if this large N series or large N expansion works, you can ask what's the leading order term. So the most important diagrams. And since this is an expansion around N equals infinity, because it's a series in 1 over N, the most important diagrams would be those that remain after you take a formal limit of N going to infinity in the theory. So this is heuristically one way to get let's say, the leading order contribution in the large N series. Now, there's a technical issue here because if you want to see what diagrams contribute at leading order, setting N equals infinity on QCD doesn't really work. And the reason is that lambda QCD scale, which I said was close to 200 MeV, this is a physical dimensional parameter of the theory. So it goes when you need to, this is an input. It's part of the definition of the theory, in a sense. And this can be computed from G and N. And what you find is that if you change the value of N, in particular, if you send it to infinity, you also change the value of lambda QCD. You can make this diverge, for instance. So simply setting N to infinity in QCD is not going to work. You need a more clever way to take the limit. And the way to do this is to define the so-called Hooft coupling. This is, by the way, all these ideas came from papers by Hooft. The Hooft coupling is called lambda, and it's equal to this particular combination of G squared, which is the original coupling, times N. And as you see here, lambda QCD depends only on this combination, lambda. So if you keep this thing fixed, this number fixed, and then take the limit, so this requires a simultaneous limit of N and G squared in order to keep lambda fixed. But if you do that, then you are guaranteed not to change the value of the QCD scale. So you're still working in the same theory. So the way you do that is that you swap in the action G square for lambda over N. And then if you just plug this into the action looks like this. And then we can look at the rules for the G dependence of the diagrams that I mentioned before, but now in terms of these new quantities. So remember, each propagator comes with a factor of G squared. It adds to the diagram, meaning when I say the diagram, I mean the amplitude associated to the process which the diagram represents. So each propagator comes with G squared, which is equal to lambda over N. Each vertex comes with 1 over G squared, which is N over lambda. And also, each closed line, so in the double line notation, it would be a line which closes in on itself. The arrow forms a closed loop. Each closed line adds an additional factor of N. Because when you compute the diagram, you sum over all possible colors traveling along the line. So for instance, if some diagram contains a closed loop like this, the color that is traveling, the color charge that is traveling along the loop could be red, could be blue, could be green. You don't know. The diagram represents the sum of these different contributions. So you add a factor of 3. So the formula you get for the dependence of the diagrams on the lambda and n is this one. You get lambda over n raised to the power, which is a number of propagators, the inverse raised to the number of vertices. So this is like what I showed before in terms of g. And additionally, you have n times the number, raised to the power of the number of loops. By the way, the actual diagrams in field theory are not just this. You have this is just a dependence on the parameters. You have space-time dependent functions and integrals to do and things like that, but that's not going to be important for us here. Here we just want to look at the dependence on these numbers. So for simplicity, we're going to stick just to vacuum diagrams, which are basically the simplest kind of Feynman diagram you can have, which are those that represent contributions to the amplitude for the system to start in a vacuum, so no particles, and to end also in a vacuum. This can sound strange intuitively, but these are called vacuum fluctuations in field theory, and they exist. You can compute the diagrams associated to this, and they are a simple way to arrive at some of the ideas that I'm moving toward here. So this is the first example of a vacuum diagram. Again, time flows horizontally. So here you don't have anything. Then at this point, you have that out of the vacuum, a gluon-antigluon pair pops out. So this is a sort of, people call these quantum fluctuations. Each of them travels for a little bit. Here, one of them emits a gluon, which is then absorbed by the other one. And then they meet again and annihilate, like an electron and a positron annihilating. Gluons and antigluons here annihilate. So if we do the counting for this process, this vacuum process, you have 3 propagators. So one here, and one in the middle. So this first factor here, you get raised to the power of 3. You have 2 vertices, which are the places where 3 lines meet, here and here, which is where the one gluon emitted 2 or absorbed 2 gluons. And you also have the sum over the possibilities of the colors which can be traveling in these lines. So you have 3 of them because one is this outer one closes here and one closes here. So you have 3 loops. So the last factor is n to the 3rd power. And then if you just simplify, you get that this diagram is proportional to lambda times n squared. Now I call this diagram planar. This is just a bit of terminology. It means that it can be written in a plane, as I've done here. This is drawn on top of a surface. I'll give an example of a non-planar diagram soon. So here we have another diagram, which is also planar, but it has more interactions than the first one. So this one, you have 2 propagators in the middle. Again, it's all three-point vertices here, because at each of these vertices you have that 3 lines join. So you can think of this as gluon and antigluon come out of the vacuum, they exchange one gluon, they exchange another gluon, and then they annihilate. There's another contribution to the, in a sense, trivial process of starting with nothing and ending with nothing. So there's another vacuum diagram. So this one has 6 propagators, because these intermediate ones here also count. 4 vertices, one here, one here, one here, one here, and 4 loops. Have 3 in the middle and the outer one. And again, if you simplify, you get a different power of lambda, but you get the same power of n squared. And this diagram is also planar. And we will see that this is not an accident. Now this one is non-planar. So you see, you can't draw it in a two-dimensional surface, so one leg has to go under and then go back to the top and attach. Now this one has the same, is very similar to this first one here in the sense that you only have one propagator in the middle, but due to the way that it attaches to the diagram, you have, again, three propagators, two vertices, same thing as the other one. But if you follow the arrows, you will see that the loop only closes once. If you follow it all the way, you will end up meeting the starting point. So you don't have many closed loops, you have just one. So the only thing that changes is this end dependence here. And once you simplify, you find that this one is proportional just to lambda. There is no end dependence. So despite having the same lambda dependence, relative to this first one, it is suppressed in the n series by a factor of 1 over n squared, which cancels this one and eliminates the n dependence from this diagram. And it is not planar. So these are hints that the large N expansion for these gluon diagrams, and again, if you want to consider not vacuum diagrams, but actual scattering processes, then you can just repeat all of these steps. I have a slide on this at the end if anybody wants to see. It still works. And these are hints that this large N expansion has a topological nature. So to see this topological nature, we can do the following. We can treat these double lines as the edges of some closed shape. So just take the diagram and you close it up into a shape. So the loops become faces of the surface, and the outer loop you close underneath the diagram. And in this case, you get just a ball with some drawings on top, which are the faces. So you get something like a polyhedron. In this case, it's a ball, but you can imagine doing something flat instead of curved for the faces, and then you would find some polyhedron, which can have holes. We'll go into that in a moment, but this one doesn't have any holes. It's just a sphere. And if you do this, the number of edges of this polyhedron, which are these strips here, will be the number of propagators for the original diagrams. And we'll call this E. The number of faces is the number of loops, because again, each loop gets closed up into a face of the shape. And the vertices are the vertices in the Feynman diagram sense. So if you do this, you will find that the formula for the diagram dependence, here I've just substituted number of propagators for E, number of vertices for V, and so on. And then you find this combination of F, V, and E. And the relevance of this is that this F plus V minus E quantity is called chi, and this is what's known as the Euler number of the polyhedron. So this is something from geometry, which was known for a long time. It is also given for closed surfaces, so something like a polyhedron, a pyramid, if you want, but any closed surface. It even works for curved surfaces, like that ball I showed. For any closed surface, it will always also be written as 2 minus 2 times the number of holes. Holes in the sense of, a sphere has 0 holes, a torus, so a donut has 1 hole, and so on. So again, the Euler number for the sphere is 2, because the sphere has no holes. For a torus, it's 0, because these two contributions cancel. For a 2 torus, if you have a surface and you build 2 holes, if you dig 2 holes in the surface, you have something which we can call the 2 torus, and then it will have Euler number minus 2, and so on. So this is a topological number. So it means that it does not change under any smooth change in the polyhedron or the shape, the two-dimensional closed shape that has it, as long as you don't change the number of holes. But you can stretch and you can create new vertices or you can create new faces or anything like that, and it's never going to change the Euler number. So here's a quick example. Let's say you have some surface which has this section. You could have more stuff coming out of this, but let's just look at this part here. Now I'm going to eliminate this vertex, or equivalently eliminate this face, this triangular face here, so that we get just this thing here. Well, if we take away one surface, one face, we have that f goes to f minus 1. To remove this edge, v goes to v minus 2 because we remove two vertices, because it's where it attaches. And we also get that the number of edges reduces by a factor of 3 because, again, you need to separate at each vertex. So here you have one, and here you have another one, and here you have one, and here you have another one. So if you remove the vertex, then you join these two into a single edge. So you get that the number of edges goes down by a factor of 2 from these legs, and then you have this one, which you just manually remove. And if you plug this into the formula for the Euler number, it does not change. You have minus 1 minus 2 plus 3, and it stays the same. So any kind of playing around you do with the number of faces or edges or propagators, which does not alter the number of holes in the surface, is going to give you the same Euler number. And recall that in Feynman diagram language, these are different interactions. You have the gluon splitting or not splitting. These are different physical processes. But the diagrams are categorized based on this quantity, which is very robust. It only depends on the topology of the surface over which you may draw the diagram. So you have that the Lagrangian expansion of vacuum diagrams is an expansion in the Euler number of closed surfaces, in the sense that you have that all diagrams which are planar, anything which is planar can be drawn, can be wrapped over a sphere. All of these diagrams have the same Euler number, the Euler number of the sphere. But according to this formula, you have that they are all proportional to n squared, like the ones I showed before. If you go back, if you go back quickly, here we see that these are planar and they are both proportional to n squared. This is because n squared, this is because 2 is the Euler number of the sphere. Now, if you have a diagram with one hole, which is that one, can be that one that I showed before, it can't be drawn on a sphere, but it can be drawn over a torus, like this. You wrap it like this, and then you go around the torus, so you don't need to go under in this sense. It lives on top of the torus. But the Euler number of the torus is 0, because it has one hole. And we did find, by counting, that this diagram is proportional to n to the 0th power. So you have this topological classification of diagrams based on the large n expansion, meaning on the dependence on this n parameter. And if you want, you can look at the diagrams that you can draw on top of the two torus, which is this shape here with two holes, and then they will have an even, they will depend on 1 over n squared, because then the Euler number will be minus 2, and so on. So the more holes you add to the surface, the more negative the power of n becomes in the diagram. So you can say that the Lagrangian expansion, again, is a sum over the topologies of closed surfaces, in the sense that you have, if you have the vacuum transition amplitude for gluons, all of the diagrams which are planar, you represent them by this Euler number 2 surface. All the diagrams which have the Euler number of the torus, You represent them by this. So this is the expansion. And the leading order term in N is just keeping the planar diagrams, because those are the ones that have the strongest N dependence. All the other ones are subdominant. Now, okay. Now I'm going to go into what's the relation of this with string theory. Again, this will be very rough, but fortunately, we don't need many of the details of string theory just to do a sketch of the main idea. Now, string theory is something very different from quantum field theory. In string theory, the fundamental objects are not particles, but strings. So a string is just a one-dimensional object, which is extended, and the string can be open, like this one, or closed into a loop, like this one. And the connection with particle physics comes from the fact that different particles can be viewed as different vibrational modes of the strings. So if you have, for instance, a closed string which is vibrating and rotating in a particular way, excited in a particular way, that behaves as a graviton, which would be the particle of gravity. An open string behaving in a particular way will behave, excited in a particular way will behave as a photon. You can do the same for gluons and many other kinds of particles. Now, at low energies, string theory is approximated by quantum field theory, in the sense that if you have something like this, where a closed string splits into a pair of closed strings, this is like a string vertex. If you're in the low energy regime, you don't have enough resolution to see the small circular direction of the string. So you basically only see a line. And so the string diagram intuitively becomes a particle diagram, because the low energies means that you're looking at the physics of large length scales. So that's, of course, an important point of connection between string theory and quantum field theory. But as full theories, so not in the low energy limit, they are quite different. And in particular, of course, there are more differences. String theory will always include gravity. In fact, it needs to include gravity for consistency. So this is a very important difference between the two. And it turns out that you can also draw diagrams to discuss string amplitudes and string interactions, the same kinds of things we did for gluons before. So here, for instance, string propagation, there is an analog of the coupling for the strings. It's the string coupling. And if the string theory is weakly coupled, the dominant contribution for string propagation will be this diagram, which is just a string propagating directly from one point to the other, just like for the particles. Here we have a string which splits into two closed strings, which travel for a bit and then they rejoin. So this is just like the gluon diagram from before. And you also have other possibilities. So it's roughly the same idea in this case as in particles, as in quantum field theory. But then you can ask, what's the vacuum amplitude for a closed string theory? So again, the vacuum amplitude is always the amplitude for the system to go from no excitations to no excitations. And the vacuum amplitude for closed strings is precisely a sum over the topologies of closed surfaces. So here you have the same drawing as before, but the interpretation is different. Instead of bunching together gluon diagrams based on their topologies, here the drawing can be taken literally. Here you have 0 strings, then a closed string pops out of the vacuum, travels for a bit, and then it closes up. This is one possible vacuum fluctuation for a closed string. Here's another one. A pair of closed strings pops out of the vacuum. Each one travels for a little bit, one above and one below, and then they annihilate. This is another contribution. You have one where this happens more than once, and so on. So this is precisely the same kind of expansion. The interpretation is a little bit different, of course, but the topological structure of this expansion is precisely the same thing that we found for the large N series for gluon amplitudes, which is quantum field theory for the strong force. In particular, it doesn't have anything to do with gravity. So this raises the interesting possibility, or the interesting question, which is the following. Is the theory of gluons secretly a closed string theory? Can we take this heuristic idea of doing a large N series to reorganize the diagrams, the gluon diagrams, the gluon amplitudes, into a topological series? Is there a string theory whose actual expansion matches this topological reorganization of the gluon diagrams? So surprisingly, the answer is yes, at least for many theories which are very similar to the theory of gluons. And this is one way to have some intuition for what AdS-CFT is. So Maldaceno's original AdS-CFT paper provides a precise realization of this idea. He found from taking particular limits of string theory, he discovered that this n equals 4 super Yang-Mills theory, which is nothing but a particular conformal and supersymmetric version of the theory of gluons. So it's a theory which is not precisely the theory of gluons, but it's like a cousin, you can say, of the theory of gluons, which is a bit easier to study. You have that this theory is precisely dual to a string theory, or closed string theory, in the sense that I showed before. The closed string theory is called type 2B string theory, which is a particular kind of string theory in a particular background. So background metric. Instead of the strings existing in flat space, they exist in a curved space, and this curved space is AdS 5. So AdS stands for anti-de Sitter, which is a particular space-time, which in terms of Einstein's equations, it's a solution of them with negative constant, cosmological constant. But the main point is that AdS-CFT is precisely a realization of this idea that theories like that of the strong force, so theories involving things like gluons, can be rewritten in terms of string theories, which are quantum gravity. It's hard to show that when one theory is strongly coupled, for instance, low energy gluons, the dual theory is weakly coupled. Of course, we don't know this for actual gluons because we don't know the actual dual theory for gluons. But in this case, for instance, of n equals 4 super Yang-Mills, you can see this very clearly. When the gluon-like theory becomes strongly coupled, so when the diagrams, when G becomes large and you don't know how to do the computations anymore, that's precisely the regime in which the string theory becomes tractable, in which you can do the string theory computations. So this represents a possible path for low energy QCD calculations, using instead a string theory dual to translate the quantum field theory language into string theory language, and then you can do the computations at strong coupling. So this is the crux of AdS-CFT. So since this paper we have learned a lot, I'll just mention briefly some points here, but I'll just give some buzzwords in case anybody's interested. You can ask more or look them up because there are many different directions in which people have extended this idea. First of all, that theory I showed before, n equals 4 super Yang-Mills, it's like the theory for gluons, but it has many non-physical aspects. Supersymmetry, a very high degree of supersymmetry, conformal symmetry, which is also another kind of symmetry which is not seen in the actual theory of gluons. So it would be nice to learn how to make this more precise, more closer to real life gluons, and then even closer to real-life QCD, which is gluons and quarks. This can be done. There are many ways to take this original duality found by Maldacena and break these symmetries in different ways in order to build more realistic models for QCD and to do some actual computations. So this has been done. You have models which go by different names. You have the hard wall model, soft wall model, this Witten-Sakai-Sugimoto model, and many others. Each of them has their limitations. This is important to state. And they usually match, at least qualitatively, what you expect from low energy QCD. You can take this also away from particle physics and try to build holographic models. These AdS CFT models are called holographic models. You can also try to apply them to condensed matter physics. So condensed matter physics in many cases also involves quantum field theory. Quantum field theory is not just particle physics, it's also useful for condensed matter, for phase transitions, for many topics in statistical physics. So for instance, in superconductivity, you can have holographic models, topological physics of matter. There's been some application on that and many other topics as well. And since the original correspondence found by Maldacena, many new pairs of QFT string dual theories were found. So it's important to state that many of these do not involve supersymmetry or conformal symmetry. Now, AdS CFT, the CFT means conformal field theory, because originally the gluon-like theory had this property called conformal symmetry, but it's not required to have an AdS CFT-like duality. So people have taken to calling it gauge gravity duality or gauge string duality or something like that. So this is very important to know, because if we want to find realistic models that use these ideas, we need to know if they depend on supersymmetry or conformal symmetry, which are not usual features of real-life theories, with some exceptions in the case of conformal symmetry. And indeed, you have dual pairs which do not have these features. So this is good news. People have also generalized these ideas to study quantum gravity in flat spacetime. So these are very modern topics. They go by the name of, well, one is celestial holography, the other is Carolian holography. These are, in a sense, AdS-CFT inspired. And there are, of course, many more directions in which people have played with these ideas over the last 25, a little bit more years, where after Maldacena's paper. And there are also very important open questions. For instance, given some theory, what is the dual pair? Can this be constructed? Now, we don't know how this is done currently. We can look for pairs and find them and do a series of tests to make sure that the duality works. And very few people currently doubt that, for the well understood cases, the duality might not be true. Many tests have been done, but we don't know how to, given one theory, compute its dual pair. So in a sense, there's a bit of guesswork involved, and we would like to have a constructive method, and we don't currently. Another open question, can the duality be proven rigorously? This is a very difficult thing to do, because you would need to compute on both sides objects and show that they are the same, but one side is strongly coupled. So we only know how to do the computation on one side of the duality. But still, it might be possible to find a proof, and at least in some particular limits, or for simple models. And the bigger question is, can this be proven for the more realistic theories? So for instance, for Maldacena's original one. And what would be learned from such a proof? So For instance, how exactly would the particle diagrams become string diagrams? What's the mechanism? How do we improve the existing models, the holographic models, or build new ones? Because again, these models still mostly do not offer new quantitative. Well, let me put it this way: they manage to capture correctly the physics of low energy QCD on a qualitative basis, but in most cases, they still get some of the numbers wrong. So these models are in constant improvement, and there are many papers on the QCD models and the condensed matter models where new methods are found and new computations are done and being compared with experiment or with lattice results, which is a numerical way to do the QCD calculations. So that's also an interesting research direction. And the big question, of course, since the beginning, is what is the holographic dual of real QCD? That hasn't been found yet, and it would be, well, it would be a major advancement if we could find this. So I'll end at this slide here. This is just to show you one possible place, which is happens to be where I'm studying currently, and Dennis as well, which is an interesting idea if anybody wants to study string theory or AdS-CFT in South America, which is the IFT Unesp Institute, which is in São Paulo, Brazil. And with that, well, I'll leave it at this. Thank you.
Thanks for your presentation, Pedro. It was interesting. So we are willing for some questions from the audience, maybe. You can also try to write something on the chat if required, or also you can also do your questions on Spanish and we can translate them to Pedro.
Well, I have one question. So, well, thank you for the presentation. It was too interesting. Well, I saw that there's a lot of topology involved in this kind of, well, in this context. So, are there other topology techniques or some related topics which are involved? For example, I don't know, maybe cohomologies or maybe sometimes I heard that knot theory is used in string theory. So I am a bit interested in if they have some relation to some of the things that you showed us.
Right. So string theory in general has many mathematical features, and you're right in saying that people have used knot theory to discuss issues in both string and field theory. But the topological the word topological that I used was used in the most simple sense, right? It's just a classification in terms of holes. And while there certainly are more advanced topological methods in string theory, in particular, this branch of string theory, which is called, well, it's called topological string theory, in which you can play around with these AdS-CFT ideas in a bit more detail, because you're working with a simpler theory. I'm not really able to give you anything too specific because I don't really know a lot about these things yet. So the answer is yes. Yes, people work on it, but I wish I could answer you in more detail, but if I try, I would probably say something wrong. But it's a positive answer. Yes, there are many topological, more advanced topological concepts and techniques being used on string theory and AdS-CFT in general. I don't know if you're aware of the Physics Latam institution. If you want, I can send it to you. They have mini courses and also larger courses. It's all online. It's relatively recent, and there are many courses related to topology in physics, topology in string theory, and things like that. So that might, and it's all uploaded to YouTube. So that might be an interesting place to look.
Yes. So is it a YouTube channel or something like that?
Yeah. The lectures all go on YouTube, but it's a online it's related to ICTP, and so you can take courses, you can apply for courses, and they give certificates. It's very nice. They are all online courses, and then after they upload the lectures to YouTube.
Okay. Yeah. I will search.
Oh, by the way, they are mostly in Spanish, which could be interesting to know.
Okay. Thank you.
Is there any other question? Okay, so maybe while we are waiting for some questions, we can take a look to the diagrams that you mentioned, Pedro, at the end of your slides.
Oh, right, yeah. These are the independents of some diagrams which are not vacuum diagrams. So these are actual corrections to the gluon propagator. So they are, in a sense, more physical. So if you do the counting, you will see that, again, the planar ones, in this case, they have a 1/n dependence. And the non-planar one, which is this one at the bottom, is suppressed again by a factor of 1/n squared. So the same idea works.
Great. This idea of large end expansion, I think it has been used on a lot of areas, right? I have seen that also. It's used, for example, when you have charges and you have to do some large end charge or something like that. Have you ever heard about that?
Large end charge. What
Yep.
kind of charge?
I don't remember actually, since I'm not very familiar with that theory, but I think this large end expansion is very useful when you are trying to do some semi-classical approach to some condensed matter
Oh yeah, yeah.
models.
Yes, condensed matter people use this because in condensed matter you have all kinds of models, and some of them are somewhat similar to the gluon theories. They have matrices, and in the gluon theory you also have matrices, right? And Yang-Mills. So in those contexts, they also do the large n stuff, or you can also do the large n expansion and vector theories, which are, by the way, simpler. So yeah, condensed matter people do this a lot.
Great. Well, do we have some other questions on the chat or people here?
Well, maybe now I have another question, and it is like, are there other topics similar to this one that you're working at the IFT? Because I know I have IFT, so I don't know if there are some similar topics to this one, and maybe which professors are working on this one, because it's too interesting.
So at IFT, there are currently 4 string theorists, or people who are working with string theories in different sense of the word, but I think most people would agree that we have 4 string theorists at IFT. You have Nathan Berkowitz, which is my supervisor, and he's also known for the pure spinor formalism for string theory, which can also be applied to these kinds of ideas. You have Pedro Vieira, who's done important work in CFT, higher dimensional CFT, using also AdS CFT. You have Andrei Mikhailov, who, I mean, they all work on this in different ways, and his work is more mathematical and more algebraic in a sense. And you have Horacio Anastasi, who has written, by the way, a large book on AdS-CFT, and he also has a lot of phenomenological work on QCD models and condensed matter. I mean, I think he has a book just for condensed matter with AdS-CFT. And currently, I think at least some of his students are working on something called holographic cosmology, if I'm not mistaken. But I mean, you can look it up on the archive. It's roughly speaking, using AdS CFT to discuss things like, well, to try to answer cosmological questions. I don't want to try to remember things off of my head and say something wrong, but you have many people working on this at the IFT with different approaches. So from the more phenomenological to the more formal or mathematical, there's really a wide range of approaches to this. You can do this from a more string theory perspective, because I didn't say this, but you can arrive at this picture from limits of string theory. So of course, string theory plays a big role, but you don't need string theory for many of the applications. So you can do this from a field theory perspective as well. And if you're interested in things like flat space holography, you also have two professors at the University of São Paulo, which is in the same city as the IFT, which have been hired recently, and they work on these topics as well, which are Eduardo Casali and Gabriel Menezes. Again, I can give you a lot more detail on any of this later if you want. You can send me a message.
Okay, thank you.
Great. So we have time for some more questions. Okay, so I assume that there's no questions. I would like to ask some questions, but well, I have already seen all of these topics on your thesis, Pedro, so I think it will not be convenient.
Good. I mean, feel free.
In principle, I have seen, as I said, I have seen all of these topics on your thesis, so I think that all these ideas we have already discussed about it. But
Okay.
if I have some questions, maybe in a pair of weeks, I will tell you.
Sure.
Great. Okay, so thank you, people, from being here, and also thank you, Pedro, for being here. Obrigado, Pedro. it was nice from you to accept this invitation, and well, also to give us this glimpse of string theory related to AdS stuff. And well, you will be also invited to some other events in the future if you're interested on give some talk in the future. So we will be glad to have you here again.
Thanks a lot. Thanks a lot. I'm really happy to have been invited.
Right. Well, people, okay, so let's go back to Spanish. Bien, gente, entonces esto sería todo por el día de hoy y bueno, el día de mañana nos volvemos a encontrar con más clases en lo que es la recta final de verano teórico y bueno, no se olviden de tomar nota del lugar y la fecha y la hora de la charla de Maldacena este viernes. Ok. Bien, gente, nos vemos. Well, see you guys.